Hello, everybody. Thank you for joining us today. You are part of the 160 people worldwide who have registered to view this webcast powered by YOL Development dedicated to micro-LED display. My name is Faisal Al-Kamasi. I'm a global sales support and coordinator for YOL Development. Before we get started with the webcast, I would like to give you some information regarding the logistics. You have the possibility during all the webcasts to submit questions. In order to do so, you simply have to use the box at the bottom of the screen labeled Ask a Question. We will answer as many questions today as time permits, and for the remaining questions, we will make a following via email within a week. We'll do our best for that. Concerning the material and contents, please note that the presentation is available and download label in the resources section. You will also receive an email after the webcast within 24 hours with a link to the recorded session. Today, YOL Development will share its analysis for you on micro-LED display. I'm pleased to introduce you to our speaker, Eric Viret, Principal Analyst, Technology and Market, Sapphire and Display. He is specialized in photonics, sensing, and display. So the webcast can start. Eric, the floor is yours.
Thank you, Faisal. Thank you for the introduction. And first of all, good morning or good afternoon, everybody, wherever you are sitting now listening to this webcast. And thanks for joining us. So the objective today is to give some sort of a really high-level overview of the status of the micro-LED industry. There's been a lot of buzz, excitement, and hype. So I'm going to try to give a clearer view of what's happening. So I'm Eric Viret. I've been with YOL Development for almost 10 years now. Worked with YOL for LEDs, displays, sapphires, etc. A lot of what you're going to hear today comes from our different reports related to displays. So we have various reports on the micro displays, reports on mini LED, micro LED. The mini LED report is coming up, I think, over the next few weeks. So I think everybody by now is familiar with traditional LEDs. They're used very broadly now in lighting application, automotive application, and even in display already as a source for the backlight units in LCD displays. In terms of chip size, as you can see, it goes, I would say, anywhere from a couple hundred of microns up to more than 1 millimeter size. And in terms of package, as you can see here in the middle, there's really a wide variety of package type available from low power, mid power, high power, and different form factors. At the opposite of the spectrum, you have micro LEDs, which is really the topic of the day. And as you can see, first of all, in terms of scale of the size of the chip, it's a completely different range. We're talking chips that could be as small as a couple of microns up to, in our definition of micro LED, we decided to stop at 50 microns. So I try to represent the chips at scale here, but of course I'm limited by the size of the smallest pixel that you can generate on your display. In terms of packaging here, you're really in what is called a chip on board configuration, when there is no package and the chip is assembled directly on the circuit board. And in terms of application, we're talking a really broad variety of mostly consumer applications, smartphones, smartwatch, potentially TVs, automotive, and also some more specialized application. In between those two, you've probably heard the term mini LED. It's a loosely defined term which describes types of LEDs that are in size, I would say, in between micro LEDs and traditional LEDs. Also, there could be some overlap. The applications are different. The two major applications are those large LED video walls that we're all used to now. The video walls that you can see in stadiums or in a shopping mall or in facade of different buildings. So that's one of the key applications for mini LED, and the other one would be to make what I would call a high dimming resolution backlight unit for LCD display. So the idea would be to have a much higher number of independent controllable zone in your backlight, as well also as a very, very thin backlight. So enabling the manufacturing of really high contrast and very thin LCD displays. So in terms of technology, those mini LED are often presented as a stepping stone toward micro LEDs. Typically for mini LED, in terms of the chip manufacturing technology, it's really just an incremental evolution. There's no fundamental change. You can manufacture those mini LED for the most in existing LED fab. For micro LED, I think the situation is quite different. Micro LED requires much more disruption in terms of both the chip design and even understanding some of the fundamental science behind the LED emissions and LED chips. Probably also a need to make the smallest micro LEDs, at least for consumer application. Probably also a need to retrofit the existing fab or even build greenfield, completely new fabs. And the reason is that there's a lot of equipment from traditional LEDs that is not compatible with the manufacturing of micro LEDs. And I'm thinking, for example, the lithography tools. You need much clean room. You need tools that don't exist in traditional LED manufacturing. So really something more disruptive here. So the talk today is really focused on micro LED. As I mentioned earlier, we have an upcoming report on mini LED. Maybe we'll do a webcast specifically on mini LED applications. So what is a micro LED display? And here I apologize if you're already familiar with that, but I see that we have more than 650 people registered for this webcast. So looking briefly at the list, I see that we have a lot of people who are probably quite new to the field. So a micro LED display, in a sense, it's very similar to an OLED display in the sense that it's self-emittive technologies. And what I mean by that is that every single pixel is a independently controllable light source that emits its own light. Unlike OLED, however, you cannot manufacture those inorganic LEDs, this LED, across very large surfaces. You cannot process and manufacture large surface like traditional LEDs, OLEDs can be manufactured in established display fabs, and that means working over substrate that are multiple square meter in size. With traditional LEDs, the inorganic LED, they're made on more traditional semiconductor technologies on wafers that are anywhere from 4-inch to 6-inch or even 8-inch. And the art of making a micro LED display really is to separate all those micro LEDs from the wafer and then assemble them on the backplane that is going to control the emission of every single of those pixels. So you can do it the way it's presented on this slide, using red, green, and blue separate LED wafers, or you can do it using just blue LEDs or even UV LEDs and apply a pattern color converter on top of the emitters in order to generate the green and the red. So what are the potential benefits of microLED? So first of all, as a self-emissive technology, it basically retains all the benefits of OLED, that is the wide viewing angle, the fast refresh rate, the ability of making curved or it is flexible backplane. But in many aspects, those microLED display could do even better, or in some cases significantly better than OLED. They're extremely efficient, so there's potential for even lower power consumption than OLEDs. They retain, of course, the absolute perfect black level, but they can also be driven much higher to extremely high level of brightness. We're talking literally hundreds of thousands of nits or candela per square meter if needed. And that compares to your typical TV or cell phone, smartphone, typically get to 700, 1000 nits. So imagine 100,000 nits. Definitely not required for smartphone or TV, but could be useful in augmented reality applications or head-up display applications and so on. They're also pretty rugged, which means, first of all, that you don't need any encapsulation technology to protect them from oxygen, air, moisture. Also means you can drive them really hard, and the correlate to that is that you don't need a lot of LED surface to generate all the light that is required for your display. So you can actually use very small emitters. And this has an impact in what we call sensors in displays. I'm going to illustrate that on this slide. I hope the slides are moving fast enough. I'm trying to pause a little bit between each slide and animation, because I know that there is sometimes a lag when we do those webcasts between what I see and what the audience sees. So sensors in pixels. So the idea is that for most applications, the size of the LEDs, the size of the emitters, as you can see here in the illustration on the top, can be very small compared to the real estate that is available for the pixels. So in the case of a TV, for example, it's likely going to be around 1% or less than 1%. And what that means is that it leaves a lot of space available within the pixel to add other components, other functions, say it could be infrared LEDs or infrared sensors, etc. So it means that you have the ability to potentially integrate all kinds of functions, could be fingerprint reader or 3D motion sensing, etc. You can integrate those functions directly into the front plane of the display, which is, I think, quite a unique potential characteristic of this technology. Not saying it's easy, but it's definitely an exciting possibility. So with all those potential benefits, no surprise that a lot of big names are invested. I think you can say it all started with Sony. We did a pretty thorough intellectual property investigation for the micro-LED display space, and Sony really the company that filed some of the earliest patents as early as the early 2000s. I think we're talking 2001, 2002. Nevertheless, it took them probably a little bit more than 10 years to show what, to my knowledge, is really the first fully functioning consumer-type display prototype. So in 2012, at the Consumer Electronics Show, the CES in Las Vegas, Sony presented that full HD 55-inch micro-LED TV. And then in 2016, they introduced that large LED video displays. Since then, you've probably heard or read news about many large companies getting involved in micro-LEDs. What probably generated the initial buzz was the acquisition of Luxvue by Apple. But since then, companies like Facebook, Google, Sharp, Intel, Samsung have all conducted some type of investments in micro-LEDs. Those big names are not the only ones. As I mentioned earlier, we've done a pretty thorough intellectual property analysis with our sister company, our colleagues at Nomade. We found close to 1,500 patents relevant to the field of micro-LED displays. more than 120 companies involved, and you can see the trend, you can see the number of patents filing, and clearly immediately notice that the activity has been increasing very quickly over the past few years. Just to be clear on the strategy for this report, we are really looking specifically at micro-LED application in displays, which is why some other studies might conclude that there are many more micro-LED in general patents than that, but we focused on patents that explicitly mention or discuss display applications. So the idea of using LEDs in the self-emissive display is not new. You're all familiar with those large LED billboards or LED video wall. The difference here is really in terms of scale. Those large display walls are made using surface-mounted device packaged LEDs that are typically about 1 millimeter in size at the minimum or much more. With micro-LEDs, we're really thinking completely different scales. And so to illustrate that, I shamelessly stole an idea from our friends at Alos Semiconductor. The idea was to compare those micro-LEDs to common atmospheric particles. And as you can see here, the typical micro-LED that we're talking about for consumer display applications is about the size of smog particles or pollen or even a large bacteria. So what that means is that if you're trying to make a 4K display, whether it's a TV or a smartphone or anything, if you're trying to make that 4K display with micro-LED, this is akin to assembling 25 million grains of pollen with a positioning accuracy of about 1 micron and doing so without a single error. So that gives you a better grasp, understanding of the challenge that is at hand here. The size is not the only problem. If you, again, trying to assemble a 4K TV and you're using traditional pick and place die bonding equipment, at this kind of accuracy, 1 micron, the throughput is typically about 1,000 die per hour. So that means that it would take about almost 3 years to assemble one TV. Of course, you can always set the takt time of your fab and then make the necessary investment. But you can imagine that the footprint of the fab and the capex required would be absolutely phenomenal. So there's definitely a need for transfer and assembly technologies that would be much faster. And in our estimate for consumer display, I think we ideally would need a technology that provides at least about 1 million die per hour. So I don't know if the slides are still moving on your side. It seems like everything is frozen on my side. I'm not able. Oh no, there it is.
That's perfect, Eric. Everything's going very good. Okay.
No, yeah, it was frozen for a second. It's working now. Thank you. So here a quick view of the key attributes of the transfer process. The first one, obviously, we just discussed is the throughput. Second one is basically the capabilities of the process. The yields, of course. What I call KGD stands for known good die, and the ability or not of a technology to basically eliminate die that are known to be defective from the process. It could be a requirement or not, depending on basically the philosophy you adopt for manufacturing. I will come back on that in a second. Intellectual property, of course, is critical, and of course the cost. So all those basically factor in and play and contribute to the cost of ownership of the technology. So we did a pretty thorough investigations, and we found literally dozens of high throughput transfer technologies. We organize those in three major families. The massively parallel pick and place. Here the idea is to do basically same thing as a traditional pick and place equipment, where a robot or a piece of equipment goes from a donor wafer to the display backplane and goes back and forth and pick up the die and position them. The idea of massively parallel pick and place is to do the exact same thing, but instead of moving one die at a time, you're going to move tens of thousands or maybe hundreds of thousands die with each process cycle. Another family is, just pausing a second, okay. Another family is what we call sequential semi-continuous process, where you have more kind of a cartridge, a bank or reservoir, whatever you want to call it, of die, and then you can move continuously or semi-continuously and kind of print the die on the backplane. And then you have some more intriguing technologies that we call self-assembly, where the die can be either dispersed in a liquid solution or floated magnetically, and then they kind of find their position themselves onto the substrate. So three major families here. For each family, you also have a pretty broad variety of ways to detach or hold the die. Could be mechanical, electromechanical, using magnets, etc. And same thing for the release force. So all in all, literally dozens of different technologies. So it's quite reassuring to know that there are a lot of smart people trying to tackle what is probably the single largest challenge for MicroLED, which is to cost efficiently assemble display with high yield. So yield is clearly a key for MicroLEDs. So the way to look at it at a very high level, we can look at the first block, which is anything upstream, anything that has to do with the die manufacturing itself, the epitaxy and the chip making, lithography, etc. And then the more downstream transfer and assembly of those micro-LED die onto the display backplane, and finally anything that comes downstream. So there's clearly going to need some yield and defect management strategies to minimize the cost and the impact of yield and limit the number of repairs. Why am I concerned with repairs? That nowadays the consumer displays have to be literally zero defect and no dead pixel. They have to be absolutely perfect. So what that means in terms of manufacturing, here I have a table that kind of shows the number of potential defective pixels for different level of yields and different displays. So if you look at the middle row here, let's assume you have a 99.99% manufacturing yield, which is already pretty good, as you can imagine. And let's say you're trying to assemble a 4K panel. This is this third column here. So 4K panel at 99.99% yield, this means that you're going to potentially have up to 2,500 defective pixels. And of course, most likely those pixels are going to be spread out kind of randomly across the surface of the display. So you probably can't use mass transfer, massively parallel transfer technology to do the repair. You have to use a individual die bonder, more or less. And what that means is that with the throughput we discussed earlier, it would take probably more than 2 hours just to repair those die. And that's assuming they are repairable, because depending on the architecture of your displays, here I'm showing an architecture where you have the back plane at the bottom, the front plane, and what you see in the middle is the LED die. So it might be that depending on your structure, the die needs to be encapsulated, and then you need a top electrode before you can actually test it. And if at this stage you realize it's defective, the question is how can you remove and plug in another die to repair that. So there's a lot that can be done to, I would say, design for repairability to make sure that die can be easily repaired, but there's also a lot that can be done to try to minimize the number of repair that you want to do. So to simplify, I would say that there are three major strategies to manage yield in micro-LED manufacturing. The first one is what I call upstream elimination of bad die. The idea is that let's assume you have a technology that allows you to test every single die on the wafer, and then you can bin the die, so remove all the bad die. And then you have a technology that allows you to selectively print or selectively assemble only the good die. So by doing so, you manage the yield upstream, you eliminate all the bad die, and you only assemble the good ones. So your overall yield is basically driven by the assembly process. So of course, to achieve that, you need some pretty efficient testing technologies, because micro-LED, if you're looking at the smaller size, we're talking possibly 500 million or even close to 1 billion micro-LED on a single wafer. So you obviously can't use traditional probe testing. You need some sort of, again, massively parallel, contactless testing technologies to do that. The complete opposite technology is basically to say, okay, it's going to be impossible or too complicated, too expensive to test every single die. So we're going to do blind printing, which is we print, we assemble every single die, but we design our system for repairability, and we just only at the end of the process test and test the whole display, which is easier and faster, and repair only the bad die. And of course, in between, you have the whole gamut of strategies that basically consist in maybe not testing every single individual die, but at least testing the wafer at a high level and figure out which areas of the wafers are likely to provide or to give too many defects, and those areas can be discarded. So I mentioned testing earlier. As of today, there's no off-the-shelf testing equipment that would be suitable for micro-LED. So what you would need is something akin to the TFT array testers that are now widely used in traditional TFT display manufacturing. We've seen some companies have started working on this. Here I have a picture from Tesoro Scientific to illustrate what it would look like. The picture you're seeing here is a mapping, a functional mapping of micro-LED at the surface of the wafer. So this is a testing that's conducted at the wafer level. So yields, of course, leads to cost, very critical, and cost is also a critical parameter for micro-LEDs. We've already seen pretty impressive micro-LED prototypes. So now the question is, can you manufacture those at high yield and at a cost that is compatible with consumers' expectation? So I'm sure a lot of you have seen or heard about that wall. It's branded the wall display that Samsung first showed at the CES in Las Vegas this year in January. So at the time they call that micro-LED TVs, and you can see here a close-up of the chips that are assembled on the display. So first of all, they're not micro-LED per se. They're using traditional size, standard LED size that are assembled in a chip-on-board configuration on the displays. If you start looking and doing some back-of-the-envelope calculation of what would be the cost of a display like that, I have a hard time thinking that this 146-inch TV would come at anywhere less than at least $150,000. So nothing that will trigger any riot at your local electronics store on Black Friday. So cost is a major challenge, and you have a lot of opportunities to reduce cost down the way through design and process capabilities. The first one, the obvious one, is the die size. The die cost or price scales with the surface of the die. And as I mentioned, you don't need a lot of surface to get the light you need. The constraint here is how small of a die can you manipulate and assemble. But if you can go for an application, say from a 10 micron die to a 5 micron die, that's already a 4-time cost reduction. I didn't mention there's another way to manage the yield, which would be to use redundancy. So instead of having 1 emitter per subpixel, you put 2 microLED per subpixel. So if one is defective, then the other hopefully will not. So if you look at the statistics, it's a very efficient management strategy. You can really dramatically decrease the number of required repair to levels that I would say could be manageable even today with today's technologies. Of course, the drawback is that you double your LED costs. So if you have a way to design a process and a display that doesn't require this redundancy, of course, you immediately have a 2x cost reduction. And then there's a lot of things that can be done with the transfer and assembly of the display. I'm going to illustrate that in the next couple of slides. So let's say you have 6-inch LED wafers and you're trying to assemble a 75-inch TV. So if you're using like that massively parallel pick and place technologies, let's say you're using a rather small stamp that is 12 by 12 square millimeter. The advantage of using a small stamp is that you have a good coverage of the surface of the wafer. You're not leaving too many LEDs on the edges of the wafer. But this means also that you're going to need about 10,000 transfer per color. So you can decide then to increase the size of the stamp all the way to the largest single stamp that you can fit in this wafer here. So then you can decrease your transfer cycle, number of transfer cycles required to populate the display to about 170. So just by optimizing the size of the stamp, you can go from 30,000 operations to about 510 operations. Of course, this supposes that you have the technologies that allow you to use those very large transfer head or transfer stamps. But you can be even smarter and use what I call here interposer, but what they are really is just an intermediate carrier for the micro-LED die. So the idea is that you use a small stamp to populate a very large interposer. That way you have the benefit of a small transfer head, which is a good coverage of the wafer surface. And with that, you populate a very large interposer, and then you populate your TV from this interposer. So in the case I'm illustrating here, which is probably a little bit extreme, if you're using a very large stamp, here I considered almost 20 centimeter by 20 centimeter. You can reduce the number of print cycles down to about 138 total. So we went from 30,000 in the previous slide with a small stamp to 138 just by clever design of the process. So you can imagine the corresponding cost reduction can be quite impressive. So of course, what I'm presenting here, this is just a PowerPoint. So it's very easy to make a perfect display at a very low cost on an Excel spreadsheet. The reality, of course, is a little bit more challenging. But this is just to illustrate that there are really credible cost-down paths for making a different type of display. So here I'm illustrating in the case of a 75-inch 8K displays. We did a lot of cost modeling, cost analysis, and this is all presented in much more details in our report. But the punchline here is that there's really a credible path for cost reduction that could allow a micro-LED TV to be cost competitive with OLED TV. So again, as I said, it's very easy to do a good and cheap TV on spreadsheet. what is the reality? Well, the reality is that there's still a lot of challenges for micro-LED technologies, and I'm not going to comment this slide in too much details. You can look at it after that at home. But basically, to the left, I listed the most pressing or critical challenges for micro-LEDs, and the arrows that you're seeing in the middle illustrate the progress that we consider have been made over the past 18 months to 2 years. And every single of those major thrust areas, the progress has been quite impressive, I have to say. There's some aspect, if you look at the third one, the chip efficiencies. Just 2 years ago, I was still seeing that as a potential showstopper. At the time, the efficiency of the smallest micro-LEDs was very often below 5%. Now we're seeing results above 20, even 30%, and companies seems to be confident that there's still room for improvement. Same thing for the epitaxy. The epitaxy requirement looked quite stringent, but over the past 2 years, I had multiple discussions with the MOCVD reactors manufacturers, the equipment suppliers for the epitaxy, and the progress and the results that they're showing are quite impressive. I would say we are not quite there yet, and probably need one more iteration of releasing new generation of tools that could be perfectly suitable for micro-LEDs. But I'm really confident that we're not going to look back 5 years from now and say, oh, micro-LED didn't happen because of MOCVD couldn't deliver. So overall, a lot of progress, some concern at the bottom. I think some downstream issues might have been overlooked by some players. The driving is one example. At the first level, you say, okay, it's a self-emissive technology, so we're going to drive that just like a no LED. But then turns out the characteristic of LEDs are quite different, and they can be much more difficult to drive. So we're not even sure, despite what most people think, not even 100% sure that it's going to be very straightforward to use the existing LTPS or oxide backplane. But this is really open for debate. I'm hearing very different views on that. But just here, the punchline is that really impressive progress over the past 18 to 24 months. But there's still a lot that needs to be done before we get to high volume commercial products. Another way to look at that is to look at the gap that is required between making a prototypes where you basically prototype something that just needs to work, where most pixels light up and you don't really care about the cost and the yield. And there's a huge gap between prototype and the consumer grade display, which has to be zero defect and perform really well under every angle, have a long lifetime. In some cases, the off-state aspect can matter. And of course, you have to manufacture that in a cost-efficient way with very high consistencies. And what I found interesting is that when we talked to really a lot of players in the field to prepare this report, and very often the companies that are really just at the stage now of presenting their first prototype, they tend to be rather optimistic and confident that they can be on the market within maybe in some cases the next 2 years. However, when we talk to companies that have presented prototypes, and often very good looking prototypes, a few years back, as far back as 5 years or more, those tend to be a little bit more conservative. So this tells me that there's a lot of challenge and work needed to go from the prototype to a really perfect consumer grade display. So I'm starting to be concerned that we might be in one of those what I call 2080 situation, where 20% of the effort gets you to 80% of the results, but then getting the extra mile that is needed for that perfect display can be extremely time and resource consuming. Sorry, it seems like it's frozen again for a second. No, there it is. So I hope you can all see the next slide. So we've talked technologies a lot. Now let's look at the supply chain briefly. It starts upstream with LED manufacturing. So there's already a pretty vibrant, thriving LED industry. The problem is that, as I mentioned earlier, for micro-LED, chances are that you might need some serious retrofit of your existing fab, or maybe even building a brand new fab. Backplane, there still is a question mark whether we will be able to use the existing LTPS or oxide backplanes. And then there is the whole downstream that basically doesn't exist yet. You can't even purchase the equipment off the shelves, and you have to set up everything from the assembly, testing, etc. So you have a pretty complex and very horizontal distributed supply chain where each process is critical. So managing every aspect will be challenging. The display makers often don't have much experience with LEDs and vice versa. The intellectual property is also quite spread out. Again, we did that study, and we found that very few companies have a highly transversal portfolio that would cover all, or at least most, of the aspects of micro LED displays. And there's also some of the earliest patents from the early 2000s that some of them might have a significant blocking power. So I wouldn't be surprised if when those micro LED come to fruition, I wouldn't be surprised if we start seeing some epic intellectual property battles. Another thing that could slow down or hinder a little bit the ramp up of those technologies is that we're in a period that I would consider akin to the Cambrian explosion in the theory of life and evolution. By that I mean that there's literally not a week or a month without a new company coming up with a new assembly technology, transfer technology, color conversion technology. So we're in a period of extremely high creativity. A lot of smart people are coming up to solve all those challenges that I briefly discussed earlier. So this is exciting. It says that we will probably find solutions for all of the problems. But it's also a double-edged sword, because it means that for a company, if a company would be wanting to invest now and try to be first on the market, it's very risky to make a choice now. There's so many technology paths that are possible, that assessing every single one of them and trying to find the best one can be a bit scary. So big decision and big technology bet if you're trying to invest now. And I think that's what still missing now, is that we still haven't seen really any micro LED companies coming up with a convincing, I would say, at least pilot level manufacturing line, something that would be able to crank up at least a few thousand displays a month with high good yield, something that would be encouraging for the future. Getting close to the conclusion of my talk now with a word on potential applications. So there's the LED video wall to the left. They're real, they already exist, they're on the market. In our definition, they're more a mini LED type of technologies. Augmented reality and head-up display is probably could be one of the first killer apps for micro LED. So they won't move the needle much in terms of total volumes, and the small displays and the volumes of devices is not that high. But in terms of performance, I actually do believe that micro LED is probably the only technology that could deliver the combination of efficiency, brightness, and form factor that would be very desirable for augmented reality applications. The smartwatch is probably the low-hanging fruit. It's a small display. The pixel density is right. You don't need too many pixels. The added value on the display is really high. So it's really a very compelling application for micro LED, and also potentially a good way to start setting up and stress testing the supply chain. The TV, I would argue, if you know how to make a smartwatch, you probably know how to make a TV, although there might be some differences in the assembly process. But the challenge for TV is more how and where do you find differentiation versus OLED, for example, or the high-end LCDs. The super high brightness is not that necessary for TVs. Efficiency is not that critical because it's not a battery-operated device. So the question is, where do you find differentiation? And the answer might lie in very large panels. I think I'm coming back on that in a second. The smartphone is also technically, once you know how to make a smartwatch and a TV, you will probably know how to make a smartphone. The major challenge with smartphone is the cost target. Today we already have OLED displays that some qualify as virtually indistinguishable from perfect. And they're starting to be more and more affordable, and with additional capacity and increased competition in the field, the costs are probably going to come down further. And we did a lot of cost modeling, and our conclusion is that it's going to be very hard to get on par cost-wise with OLED. So it means that you need differentiation in terms of the performance. So for MicroLED to succeed in smartphone, you probably need to be able to come up with something that no other display technologies can deliver. And this could be related to those sensors in pixels that I mentioned earlier. I just mentioned TV. So here I want to look quickly at the opportunity for very large displays. If you look at very high level, the major cost driver for a TV are the two main components, the TFT, the thin film transistor backplane, and the front plane, whether it is LCD or LEDs. So with traditional display technology, this is the first column, both of those cost contributors scale with the surface. If you're using MicroLED, you already have some change here because the backplane remains the same. If it remains the same, then the price cost scales with the surface. But for the front plane, it doesn't scale with the surface anymore. It scales with the number of pixels. If you have a 4K display, you have about 25 million LEDs, and the cost is the same whether you're spreading them out on a smartphone backplane or on a large TV backplane. But you could imagine something even more disruptive and take advantage of this real estate that's available. And instead of using a TFT backplane, you can imagine having a small integrated circuit, small ASIC that drive every single pixel, and you have enough room for most applications to position those driver ICs. For your information, that's actually the technology that we believe is used in Sony CLED LED video wall, except at a larger scale. So if you do that, then you have potentially a technology where the cost doesn't scale with surface anymore, but only with the number of pixels and the number of micro drivers. That means that you could save the cost of the mechanics, the printed circuit boards, and so on. But you could basically potentially make a 110-inch TV for the same price as a 65-inch. So conclusion, and try to come up with some sort of roadmap for this micro-LED technology for consumer application. I think we're entering now, we'll soon be entering what I call here the phase 0, which is that we're going to see maybe as early as next year some really high-end premium, could be TVs, for example. It seems like Samsung is working for next year on a 75-inch TV that would be made from micro-LEDs that would be about 30 to 50 micron in size. This is not going to come cheap, even if it's commercialized. We're probably talking a couple tens of thousands of dollars. So nothing is going to change the needle in terms of market share of micro-LED industry, except it's basically planting a stick on the ground and say, okay, this technology is real. But really for high volume consumer displays, I really don't think that anything will be ready, at least nothing significant in terms of volumes by at least around 2021. And the first candidate could be the smartwatch. Maybe there's some also interesting compelling case for automotive displays or some specialty displays. And then hopefully those first products will help test the supply chain and iron the latest details and finalize and ramp up so that we can really see consumer product. And if everything goes well, maybe the technology could proliferate through many applications. Here I have a separate parallel track for what I call the micro displays, monolithic displays. I mentioned augmented realities earlier on. With all that, we still have to keep in mind that MicroLED is trying to come in an already crowded market, so we have to understand that the incumbent technologies also keep improving. OLED costs are coming down, capacity is increasing, there's increased competition, the performance might come up as well with new material, new blue materials such as the TADF or fluorescent, phosphorescent blue. So manufacturing technology improving also, maybe a disruptive transition to inkjet printing or solution printing manufacturing of OLEDs. So this concludes our webcast today. I think we still have a little bit of time for questions. I'm handing the mic back to Faisal in Lyon.
Thank you very much, Eric. This is a very interesting presentation. Yeah, we have about less than 10 minutes. Let's go for this Q&A session. We won't be able to answer all the questions we have, but we will do a following up via email on the remaining question. At least let's try one or two questions we have. So Eric, we have one question. There is still micro LED product on the market. Have there been any significant advances over the past 12 months?
Yeah, so there's definitely no products or no high volume products on the market. So there's been a lot of technology advances that I illustrated in a few slides back. Literally in every single aspect of the technologies have made significant progress, but I agree that what's still really lacking that I haven't seen is a convincing pilot line and companies that would be able to crank up thousands of displays. So we are at a critical node, I think, where a lot of companies are probably assessing but also a bit hesitant to invest in one technology path or another. And there's some enabling technologies that are being developed but are not ready yet. You cannot purchase off-the-shelf equipment. So as of today, if you were to manufacture in volume, you would pretty much have to design and make your own equipment or partner with other players. I mean, the closest I've seen to that for now, but the application is more mini LED than micro LED, is the partnership between Rohini, a mini LED startup in Boise, Idaho, here in the US, that has partnered with Kulik and Sofa, one of the leading semiconductor equipment maker in Singapore, and they just announced an assembly technologies that is more mini LED specific. So we need to see more of that, and that's true also for testing equipment. We probably need to see more of that before we actually get high volume products in the market. Of course, there's the companies that are like fully integrated and more or less a black box. Companies like Apple, obviously, we don't know where they stand exactly and where they are. But all we can tell now is that there's no product on the market yet, and we are not really seeing any sign of a massive capacity ramp up. Because as much as Apple likes to do everything and control everything internally, they will need some partners to ramp up the supply chain.
Okay, thank you very much. Let's go for another question. Samsung announced a TV in collaboration with Play Nitride. What price point can we expect?
Yeah, that's a good question. So there's so I don't know if it was actually a formal official announcement, but there were enough rumors that Samsung is working on probably 75-inch micro-LED TV that would be basically kind of a scale down of that display they showed at CES last year, the wall. So smaller display size, but also using much smaller die size. The initial display was using die that were about 120 by 220 micron. For the new prototype / TV, we're talking about probably 30 to 50 micron die size. So as you can imagine, that's already a significant reduction in terms of the die cost. And also they're probably going to be using a smaller pitch, which makes the transfer and assembly technology more efficient in many cases. So just looking at the back of the envelope, making back of the envelope calculation, just calculating the total surface of die and assembly time, it's hard to think that this TV, if it is commercialized, would come at less than, I would say, at least 10,000, most likely more like a couple 10,000. $. So something that some people would happily purchase and afford if the result is the performance of the display is absolutely stunning, but definitely not a high volume consumer product.
Okay, thank you, Eric. We have maybe 2 minutes for maybe a last question. Are mini LED a stepping stone toward micro LED or a complete different technology?
Yeah, so yeah, it's often presented as a stepping stone. I personally really don't see it that way, in a sense, again, that those mini LED technology-wise, in terms of the chip technologies, they're really just a scale down of existing LEDs. There's none of the major disruptions that are required for micro LEDs. The only kind of bridge maybe is that to cost efficiently assemble a mini LED product, whether it's a backlight unit or a LED video wall, you can do it as of today using the existing transfer technology, pick and place, die bonding technologies, but they're really not sufficiently efficient cost-wise, and they're also a challenge when you need to assemble die that are more spread out across a larger surface. So for mini LED to commercially exist and be made in a cost-efficient way, there is a need for new transfer and assembly technologies, and those transfer and assembly technologies might indeed be a stepping stone toward even faster and higher throughput technology that could be used for micro LEDs. But in terms of the chip technologies and basically in terms of the market dynamic, I think that they're really separate things.
Okay, thank you, Eric. So we are running out of time, so the webcast is ending. So within the next 24 hours, you will receive an email that will include the recorded session. Please feel free to share the presentation with who will benefit from the information that has been presented, and you will find our analyses and reports on iamicronews.com. Thank you for joining us today. Do not hesitate to contact us if you have additional questions. You can find your appropriate contact on the last pages of this presentation. Have a good day, and we wish to see you soon in our next webcast.